Ladies and gentlemen, welcome to lecture number 21. Well, in this lecture, since I forgot that there is the Easter holiday, I will decided to record this by myself. So in this lecture, we will be talking about, I'd like to continue with some of the examples from last time when we dealt with some functions, some rational functions, and we wanted to see whether what are the horizontal and vertical asymptotes, and also to graph those functions. And then in the second part of the lecture, we will be dealing with the L'Hopital rule. This rule is a pretty amazing rule. It will teach you how to take limits of functions, especially when we have rational functions. You will see that derivatives will be involved. And in fact, the rule is pretty easy to state and also to apply. And like I said, in the second part of the lecture, we will be doing plenty of applications where we will use L'Hopital rule. And you will see how we will deal with the indeterminates such as infinity over infinity, 0 over 0, or even other indeterminates. All right, so let me get started. First, I'd like to, just like I said, to continue with some examples from last time. So I'll go back to last time. And remember, we had this, this function here, right? And we wanted to find the vertical and horizontal asymptotes of this function here, right? This was our function. F of x is 4x minus 2 over x minus 3. Okay, and then we said that for taking the horizontal asymptote, the only thing we need to do is just to take the limit at infinity, and then the value of that limit will be nothing else than just the horizontal asymptote. So in this case, we've seen that y equals 4 is a horizontal asymptote. And also, before that, we have seen that x equals 3 was a vertical asymptote, as you can see right here. Right? All right, so this function, this rational function, 4x, f of x equals 4x minus 2 over x minus 3, has a vertical asymptote, x equals 3, and y equals 4 is a horizontal asymptote. Well, given the fact that we have seen the properties of this function, the question that we need to address is, can we sketch the graph of f? Well, let's see. So what do we know at this point? Of course, we can sketch the graph. So we know that x equals 3 and y equals 4 are both vertical and horizontal asymptotes respectively. So let's draw them. So I will draw this, right? This here. Let me draw this is the horizontal, this is the asymptote right here, right? Y equals 4. And this guy here, okay, so we have this. Well, let's see, what do we know? So if we compute the derivative of the function, right, and I'll leave this to you as an exercise to figure this one out. Well, when you compute the derivative of this function for 4x minus 2 over x minus 3, keep in mind that you need to apply the quotient rule, right? So when you apply, when you take the derivative, so let me write this, f prime can be computed by the using the quotient rule. So you can compute this using the quotient rule. And of course, as you can see, you have two functions there. So I'll leave this to you as an exercise. I'm sure you can do it. Well, in other words, as you can see, the function at the end of the day, it will be given by this. So as we managed to deal with some tricky algebra there, well, not so tricky, but anyway, some algebra, we'll end up with the derivative of f being equal to negative 10 over x minus 3 squared. All right, great. Well, if you look at this quotient here, it's quite clear since the bottom x minus 3 everything squared is positive and the top negative 10 is negative, the entire thing will be negative. In other words, if we want to talk about the monotonicity of the function, you will see that it doesn't matter. It will be decreasing on the entire real line except that number x equals 3. So the f will not touch x equals 3, as we have seen that it's a vertical asymptote. So in other words, the function will be decreasing on this union of these two intervals. So it will be negative infinity 3 and 3 positive infinity. All right, great. What about relative min or max? Well, it looks like there is no relative extrema since the equation f prime of x equals 0 does not have any solutions. So no relative extrema. So f prime of x cannot be 0. So there is no x such that f prime of x is 0. So no relative extrema. Great. And now let's see, what can we say about the concavity, the intervals of concavity? Well, if we compute the second derivative, and I'll leave this to you as an exercise, right? It's just taking the derivative of the first derivative. Well, we'll end up with this. So the second derivative of f is 20 over x minus 3, everything cubed. All right. So the second derivative all the way up to 3 is negative. So you will have the here negative. And then here you will have that f, for x greater than 3, this is positive. So the function will be concave down on negative infinity 3, as you can see it here. And it will be concave up on the interval 3 infinity. And now at this point, I think we can draw the graph. And let me just do it, right? And there is no inflection point because f of 3 is not defined. So there is no way to find any inflection points where the function will be concave up or concave down. So in other words, these two graphs will look like kind of disconnected, as you can see here, this portion right here. You can see it will not touch the line, right, the asymptote. And the same thing will happen here as well. So it will go like this, as you can see. Ooh. All right. So this is how the graph of the function f will look like, right? So you have the two asymptotes, they'll not be touched, and one of them is concave up, and the other one is concave down. All right, beautiful. So this is how we deal with rational functions. So when we deal with rational functions, you always look not just for intervals where of monotonicity, where the function is decreasing, increasing, or for relative extrema, min, max, whatever. Or you also look, and not just for the intervals of concavity, so where the function is concave up, concave down, and inflection points, but also you look for asymptotes, for vertical and horizontal asymptotes. All right, let's see another function. And I would like to draw your attention with the following function. Again, this is a rational function. You can actually compute this if you want. You can make it look like, so this will be x minus 4 plus x everything over x minus 4. Or if you want, this will be equal to 2x minus 4, everything over x minus 4, right? So either way, you're gonna, you can present this function as 2x minus 4 over x minus 4, or you can write it as 1 plus x over x minus 4. All right, so let's see. So we'd like to do the same thing. We'd like to graph this function. So in order to graph this function, we'll have to look for everything. So we'll have to look for the asymptotes, vertical and horizontal asymptotes. we will have to look for the intervals of monotonicity. So in other words, we would like to see whether the function is increasing or decreasing. We would like to see, we would look for the relative extrema, so where the function has a min or a max, whatever. We'll look for the intervals of concavity, so where the function is concave up, concave down, but also we'll look for the inflection points where the function changes its concavity. So it's from concave up becomes concave down and so on. But not just that, like I said, we have to look for asymptotes as well. So as I said, we can rewrite this function as f of x equals 2x minus 4 over x minus 4. Well, and as you might guess, it's pretty clear how to deal with, how to find vertical asymptotes. So that's the first thing that we will need to do. So we'd like to find asymptotes. And like I said, there is two of them. There is the vertical and the horizontal asymptotes. First, let's find the vertical asymptote. So the vertical asymptote, we need to find the vertical asymptote, we need the following. So we need the value of x when the denominator of f of x is 0. Right, so that's what we need to do. In other words, what is the denominator? Well, the denominator of this fraction, as you can see it here, is right, this guy is x minus 4. So in other words, we would like to see when x minus 4 equals 0. So this means that x will be 4. So this is what this is the vertical asymptote. Vertical asymptote, okay. And also, if you take the limit as x approaches 4 from the left of f, it will give you negative infinity, right? So in other words, you can say that the limit as x approaches 4 from the left, right? So this means that x approaches 4 for values of x less than 4 of f of x. This will be nothing else than just the limit as x approaches 4 minus of 2x minus 4 over x minus 4. And this guy here, if you look closely, this will be, as you can see here on the bottom, you have 4 will be 2 times 4 minus 4, whatever this is. And here I have 4 minus 4. And this guy here, this guy will give you 0 minus, so this will be negative infinity. And the same goes for the limit as x approaches 4 from the right. So the right-hand limit of f of x, this would be positive infinity. So I'll leave this to you as an exercise to figure this one out. So, and as you can see, this is these two facts are stated here. So at this point, we know what the vertical asymptote is. So x equals 4 is a vertical asymptote. So let's keep this in mind. So this is a vertical asymptote. We need to know this. All right, now let's go for the horizontal asymptote. So for the horizontal asymptote, we're gonna do the following. So we need to, since in the case of vertical asymptote, we needed to see where the denominator of f is 0. Now, in the case of the horizontal asymptote, especially when we want to find the horizontal asymptote, we need to take the limit as x approaches infinity of f. In other words, we need to take the limit as x approaches infinity of 2x minus 4 over x minus 4. Well, and we have seen this last time, how to deal with these kind of limits. Well, let's deal with these limits again now. So this guy here, you see we have a fraction. So this guy is the limit as x approaches infinity of 2x minus 4 over x minus 4. And let's look on both the top and the bottom. And we would like to look at the monomials of which have the greatest power. So this is x, to the power 1, and also this is x to the power 1. And we're going to force as a common factor those monomials both on top and the bottom. So we're going to do the following. So this will be the lim as x approaches infinity of x times. And here what we will have is that this will be 2 minus 4 over x, everything over x times 1 minus 4 over x. So what I did here is just I forced the on both the numerator and the denominator x to the greatest power, which is x to the power 1. So x will cancel, and this will be nothing else than just the limit as x approaches infinity of 2 minus 4 over x, everything over 1 minus 4 over x, right? So this would be, if we plug it in, so this guy will, 4 over x will converge to 0, so this would be 2 minus 0 over 1 minus 0, which is 2. So the horizontal asymptote, so that's exactly, it will be 2. As you can see, the limit is 2 here. Anyway, you can also multiply and divide by 1 over x. It's basically the same procedure. As you can see here, I obtained the same thing as here, right? But I think it's much more natural for me to tell you how to find this. Instead of telling you that I'm going to multiply and divide by 1 over x, I'd rather say that we're going to force a common factor on both top and the bottom. So that's what you do when you deal with limits involved when x approaches infinity. So keep this in mind. This happens when x approaches infinity. So when x is large enough. Okay. And also, if we want this, so this happens when x approaches positive infinity. At negative infinity, it will be the same thing. So the value will be 2 again. So the two values will be the same, will coincide. And therefore, here we go. We can say that y equals 2 is a horizontal asymptote. So that's the thing that we would like to keep in mind. All right, beautiful. And now we would like to see something else. So we have this function again, right? It's 2x minus 4 over x minus 4. So we know the asymptotes. As you can see, y equals 2 is right here. Let me draw it. So this is y equals 2. So let me just draw the asymptotes. In fact, no, let me use the usual color. So this is the y equals 2 asymptote, right, is the horizontal asymptote, and the vertical asymptote is this one here, x equals 4. It's right here. All right. So the graph will not touch these. And now we'd like to see what the function, the intervals of monotonicity. We'd like to see the relative extrema, if there is some. Probably there is none. We'd like to see the intervals of concavity, and also we would like to see if there are any inflection points. So again, if we take the derivative of this function, well, the first derivative of this function, and again, I will leave this to you as an exercise. So the derivative will look like this. So f prime of x, well, again, we apply the quotient rule. So here, let me just say that I make myself very clear. This is the quotient rule, right? Because we have, this function is defined as the quotient of two functions, right? Let's just say g of x is 2x minus 4, and h of x is x minus 4. And g prime of x is 2, and h prime of x is 1. So again, as you can see, by applying the quotient rule, we get this guy here. That's what we get. Well, this guy is negative, as you can obviously see, right? We have a negative number over a positive number, so that would be negative. Well, the derivative will be negative no matter what. Will be negative on the entire real line except the point x equals 4. Well, since the derivative is negative, then this means that the function is decreasing, and it will be decreasing on this interval here. So negative 4, negative infinity 4, and 4 infinity. So except, so we'll have the derivative is negative. except this 0.4 here. So that's the problem. Anyway, now we can do the same thing. So if we would like to see what's the situation, how with the relative extrema, well, there is no relative extrema, no relative max and min. So we don't need to worry about this. And now for if we'd like to see how the function is concave up, concave down, well, again, we compute the second derivative. And the second derivative will give you, well, again, I will leave this to you as an exercise to see that is 8 over x minus 4 cubed. And it will be concave down on -∞4 and concave up on 4 infinity. Again, this will never be 0, as you can obviously see, because f of 4 is not defined. So there is no inflection point. And now we can easily draw the graph. And the graph will be something like this. You can see this portion. Well, it shouldn't touch the graph of f. And the same thing will go here. Oops. Again, it will not touch the horizontal asymptote. Okay, so that's the graph of f. Anyway, I didn't draw it the way I should have, but well, imagine that that is actually a continuous line. It's not interrupted like it seems. All right. So this is what this sums up what I wanted to do from last lecture and this lecture. And now we will move to what we call, this is, like I said, one of the most important things in our course, among other things. And fortunately for you, it will be a pretty direct and easy method that will allow you to find limits of functions. So, and for certain indeterminate forms. And we'll see, I will start with two indeterminate forms. I will deal first with infinity over infinity and then with 0 over 0. So this rule is L'Hopital rule. All right. So let me start first. Let me dive in and tell you what are these indeterminate forms. I think I've mentioned a couple of times in previous lectures how to deal with these indeterminate forms. But now we will see, like I said, in the first instance, we will deal with these two. Well, as you can see, they're written in various forms. So, but in other words, we will only deal with these two indeterminate forms. So it's basically infinity over infinity and 0 over 0. So these are the first two that we need to deal with. And the L'Hopital rule will address at first these two indeterminate forms. So in other words, what we need to do is the following. So we need to evaluate the limit of that quotient there. So the limit as x approaches c, a number c, of f of x over g of x. Well, you know that the limit of the quotient is the quotient of the limits. So this will be nothing else than just the limit as x approaches c of f of x over limit as x approaches c of g of x. And when we evaluate this quotient, so when we evaluate this limit here and this limit here, so when we evaluate these two limits, we might end up with these indeterminate forms. Well, like I said, roughly speaking, there are just two, infinity over infinity or 0 over 0. But to be more exact, it can look like infinity over infinity, 0 over 0, positive infinity over positive infinity. You can have positive infinity over negative infinity, or negative infinity over positive infinity, or negative infinity over negative infinity. In any case, I will just say that I will put all this together into this infinity over infinity, right? Whatever the signs are there. So such limits are called indeterminate forms. So we would like to see if we can get rid of this and how to get rid of this. Well, and there is this amazing rule that comes into play. And like I said, this is L'Hopital rule, which basically tells you the following, more or less. It tells you this amazing thing that if the limit of f of x over g of x as x approaches c, right, produces an indeterminate form, then the limit as x approaches c of f of x over g of x will be nothing else than just the limit of f prime of x over g prime of x as x approaches c. Wow, that's pretty amazing. So in other words, when you have the limit of the quotient here, right, is the same thing as the limit of the quotient of derivatives. Well, but provided that this limit actually, if it exists, if the limit of the derivative of the quotients actually exists. So this is a huge assumption, right? So once again, the limit as x approaches c of f of x over g of x is the limit as x approaches c of f prime of x over g prime of x. Okay, so we would like to see examples, and over the course of this lecture, we will see plenty of examples. And first, I would like to dwell on examples which will involve these two indeterminate forms, infinity over infinity and 0 over 0. And we will see how we can relate others as well to these two indeterminate forms. But anyway, we'll get there. But first, I would like to see how to deal with indeterminate form 0 over 0. And by the way, let me say this so that I make myself very clear. This will be a very important topic for you for the final exam. So you better pay attention to what am I about to say on this lecture. All right. First, let's start with a celebrated limit. We have seen this plenty of time, and you had to use it in the midterm exam. So I'll start with the indeterminate form 0 over 0. And the first limit that I have in mind is the following. So is the limit as x approaches 0 of sine of x over x. Right? Remember, this limit is actually 1, right? We've done this, but I told you that we will see the actual proof when we deal with the L'Hopital rule. Well, let's see. Why do we have an indeterminate form here? Well, if we plug in x equals 0, so as x approaches 0, sine of x will be sine of 0, which is 0. And, well, x will be 0, so we'll deal with 0 over 0. Well, fortunately for us, the L'Hopital rule comes in to rescue us. So I know that f of x is sine of x, and I know that g of x is x. And this. Now let me go back to L'Hopital rule, which is right here, as you can see. So if the limit of the quotient, which produces an indeterminate form, which in our case produces 0 over 0, then the limit of the quotient is the limit of the quotient of the derivatives. Wow, so great. So in our case, if we look, the derivative, so f prime of x is cosine of x, and g prime of x, sorry, is 1. So in other words, we will see that the limit as x approaches 0 of sine of x over x will be the limit as x approaches 0 of sine prime of x. So so this is, so that I will be even clearer, sine of x prime over x prime. Well, sine of x prime is cosine and x prime is 1, so the limit is 1. Finally, we proved this. Again, what if we have something like this? What if we would like to find the limit as x approaches 0 of sine of 2x over 3x? Again, we can use the first one, but we can also use L'Hopital rule. And since we discussed L'Hopital rule, why not use this. Again, in this case, the function f is sine of 2x, and if we compute the derivative of this guy, is nothing else by using the quotient rule, right? Let me just put it here. So f of x is sine of 2x, and g of x is 3x. Well, by the chain rule, sorry, I said quotient rule, but it's actually chain rule. So by the chain rule, this will be 2 times cosine of 2x, and g prime of x is 3. All right. Again, the limit of the quotient will be the limit of the quotient of derivatives, and we have this. So as you can see here, we have 2 cosines. So the limit as x approaches 0 of sine of 2x over 3x will be the limit as x approaches 0 of 2 cosine of 2x over 3. And now we can plug it in, x equals 0, which will give us 2 over 3. So that's the limit. All right, let's see another one. What if we have something like this? What if we have the limit as x approaches 2 of x to the power 7 minus 128 over x cubed minus 8, sorry. So first, what we need to do is we need to plug in x equals 2. So if we plug in x equals 2, we have 2 to the power 7, which is 128. So we'll get 2 to the 7 minus 128, which is 0, over 2 cubed minus 8, which is again 0. So indeterminate form here, it's again 0 over 0. And again, we will take the function f of x is x to the power 7 minus 128, and g of x is x cubed minus 8. So f prime of x is, if we take the derivative of this guy, is 7 times x to the power 6, and g prime of x is 3x squared. Again, by applying the L'Hopital rule, we will get this. So this will be the derivative of this, which is 7x minus 6, as you can see it here, 7x to the power 6, and then on the bottom, this will be the limit of the g prime, the derivative will be 3x squared, which is this guy here. Great. Now we can cancel some x's there to some powers, and we'll end up with the limit as x approaches 2 of 7x to the 4th over 3. And now we can plug in x equals 2, and then we'll end up by just algebra, doing some algebra with 112 over 3. So these are some examples of how to deal with limits of functions in the indeterminate form 0 over 0, and how easy it is to deal with them using L'Hopital rule. All right. Now let's see some examples with the other indeterminate form, infinity over infinity. And the first example I have in mind is this one here. I think we have dealt with this without using L'Hopital rule, right? So if you look at this function of this limit, sorry, you can actually do this without L'Hopital rule. So let's do it without L'Hopital rule, and then you will compare the two methods, and then you will decide which one you do like to use. Sometimes it's better to have more methods in dealing with a problem. So this one here, we can actually do this as so this will be the limit as x approaches infinity. And what did we say? So we identify on both top and the bottom the monomial, which to the greatest power. So on top it's x squared, on bottom is x squared. We're going to force x squared here, and this will be x squared times 3 plus 2 over x squared. And on the bottom we will have that this is x squared times 4 plus 7x over x squared. So this would be the limit as x approaches infinity. Well, we can cancel these two, of 3 plus 2 over x squared, everything over 4 plus 7 over x. Great. And at this point, this guy here, 2 over x squared as x approaches infinity, this will go to 0, and the same goes for this one here. So this would be nothing else than just 3 over 4. So the value of this limit is 3 over 4 without using L'Hopital rule, right? But also let's do L'Hopital rule. So let's identify the two functions. So in our case, this would be f of x is 3x squared plus 2. G of x is 4x squared plus 7x. So f prime of x is 6x, and g prime of x is 8x. Great. 8x plus 7, sorry. Great. As you can see them, so the limit as x approaches infinity of 3x squared plus 2 over 4x squared plus 7x. This is again, if you plug in infinity, it will be the indeterminate that we deal with is infinity over infinity. So by applying here the L'Hopital rule, LH, let me put it like this, that limit will be nothing else than just the derivative of 3x squared plus 2, which is 6x, over the derivative of 4x squared plus 7x, which is 8x plus 7. Again, we don't have to stop here. We apply L'Hopital rule one more time, so we can apply as many times as possible. Again, the derivative of 6x will be 6, and the derivative of 8x plus 7 would be 8. So it will be the limit as x approaches infinity of 6 over x, but this is just a constant, which is 6 over x, and 6 over x is nothing else than just 3 over 4, which is the same thing as you have seen here, right? So you apply L'Hopital rule twice. Let me put it here. So this was an example when you apply L'Hopital rule twice. You can apply even 3 times, 4 times. If I give you, for example, let's say if I have, instead of quadratic polynomials, polynomial on both the top and the bottom, what if I have something like degree 3 or degree 4 or 5, whatever, and you can apply L'Hopital rule many times, as many times as possible. So don't just stop after one application, especially if you don't get anything. Because you see, once we applied it once, we ended up with the limit as x approaches infinity of 6x over 8x plus 7. You see this one here. And again, if we plug in x infinity here, we will have infinity over infinity. So you don't need to stop with only one application. You can go further on with the second application, and you keep going. So, all right, now let me draw your attention with another example. And actually, I think I said this in a previous lecture, right? When we dealt with those function, the tower of power, which one crosses the first one, the infinity line. And we have said that the logarithm is the one that crosses the infinity line last. In other words, you could have a pretty much an idea of what the result of this limit would be. In other words, as x is large enough, ln of x is also large enough, and also the cube root of x is also large enough, but what if the cube root of x is much, much larger than ln of x? In other words, what if the cube root of x crosses the infinity line way faster than ln of x? And we can say this, so we can say that ln of x is less than cube root of x. In other words, when we say this will be equivalent with saying that the limit as x approaches 0 of ln of x over cube root of x is 0. Let's prove this. So if we clearly we deal with the infinity over infinity indeterminate form, and now we can apply L'Hopital rule. So in our case, let me just say the functions. on the functions. So in fact, I can delete this here because we will prove this. So the functions are f of x is ln of x, and the function g of x is cube root of x, which is x to the power 1/3 if you want. So f prime of x is 1 over x, and g prime of x, if we compute this, so this would be 1 over 3 times x to the negative 2/3, right? So these are the two derivatives of this function. So let me just box this one. So the derivatives of f and g. All right, so let's do it. We apply L'Hopital rule, and you can see that the limit of the quotient, so the limit of as x approaches infinity of f over g, f of x over g of x is nothing else than just the limit as x approaches infinity of f prime of x over g prime of x. Well, as you see, they're already there, the derivatives, we computed them. So we end up with this. And if we do some algebra here, by just doing algebra, we will end up with this limit. And as x approaches infinity, clearly the result is 0, right? It's 3 over infinity, cube root of infinity, which is 0. So this was an example. Now let me give you of an indeterminate form, infinity over infinity. So I gave you 2 examples. And now let's see some other limits. So at first, we have seen examples of the 2 indeterminate forms, 0 over 0 and infinity over infinity. And now let's see more examples. All right, I want you to look at this one here. So we need to find the limit as x approaches 0 of x minus sine of x over x cubed. So I'll give you a little bit of time to think of this. Well, let's see. We need to plug in x equals 0. So let's do that, because we would like to see what kind of indeterminate form we're dealing with. So once we plug in x equals 0, we will get what? X 0 minus sine of 0, which is 0 over 0 cubed, which is 0. So the indeterminate form is 0 over 0. Great. So we're in a good position to apply L'Hopital rule. So let's say that f of x is x minus sine of x, and g of x is x cubed. Great. F prime of x is 1, is the derivative of x, which is 1, minus sine of x prime is cosine, so it's 1 minus cosine of x, and g prime of x is 3x squared. All right, great. So these are the derivatives. So in other words, the limit as x approaches 0 of f of x over g of x is the limit as x approaches 0 of f prime of x over g prime of x, right? So as you can see, the derivatives are given there. Well, now let's see. Again, we applied L'Hopital rule once. So let me write it here. And let's see what happens now. So let's plug in x equals 0 again into this limit. So we'll have 1 minus cosine of 0. Cosine of 0 is 1, so 1 minus 1, which is 0, over 0. So again, we have this indeterminate form 0 over 0, as you can see here. Great. We can take the derivative again. So let me write it here. So f second prime of x will be what? Will be negative cosine prime, but cosine of x prime. Cosine is negative sine, so this would be sine of x. So negative sine of x, which is sine of x. And g second prime of x is 6x, right? No problem. So we keep going. As you can see here, so I have sine of x, negative sine of x over 6x. Again, if we plug it in, is 0 over 0, so we can apply L'Hopital rule again. Or you can just take out 1 over 6 out, so we know that this is 1. So the value is 1 over 6, right? Again, first of all, I want to stress this out. We need to check the indeterminate form. This is important. Right from the beginning, if you don't check the indeterminate form and you just apply L'Hopital rule like this without checking anything, then you might end up with some crazy results. Now, let me give you an example in this sense. So first, let me look at this guy here. So we need to find the limit as x approaches, because there is a danger that there's a trap that you might fall in. So, and I would like to illustrate that through this example. We would like to find the limit as x approaches 0 of 1 minus cosine of x over secant of x. And now first, let's plug it in. So we know that as x approaches 0, cosine of x will approach 1. So we have 1 over secant of 0. But secant of 0 is 1 as far as I'm concerned. So we would have the following, 1 minus 1 over 0. So it would be 0 over 1, which is 0. So this is not an indeterminate form, it's not 0 over 0. So there is no point of view to apply L'Hopital rule. So the moral of this example is to always check the indeterminate form. So that's the moral of this example, right? So always check that, always. All right. So first we have seen how to deal with these two indeterminate forms, 0 over 0 and infinity over infinity. But like I said, the L'Hopital rule will not just stop there. So it will keep going, and it will, you will see that there will be a way for us to make other indeterminate forms to make them look like these two, like 0 over 0 or infinity over infinity. But first, let's see what are the other indeterminate forms. And the other indeterminate forms are the following. So, as you can see, there are other 5 of them. And let me put this in a corner, infinity over infinity and 0 over 0, so that, because in total there is 7 of them. So these are the two indeterminate forms that we have talked about, infinity over infinity and 0 over 0. But there are other indeterminate forms. So for us, for example, infinity times 0, or infinity over minus infinity. So infinity over minus infinity will not be 0, so pay attention. This is an indeterminate form. Or 1 raised to the power infinity, or 0 raised to the power 0, or infinity raised to the power 0 will not give you 1. So pay attention. So these are the indeterminate forms. So make sure when you have a limit of function, you plug it in exactly where x goes to. And if you get one of these indeterminate forms, then you will have to deal with them. And I'll give you some examples of how to deal with these indeterminate forms. So as we have seen, you can deal with these two here, with infinity over infinity and 0 over 0. But now let's see if we can do with the others as well, with these here. So there are 7 indeterminate forms in total. That's what you need to know. There is 7 of them. All right, great. Now let's see any examples for each one of them. And the first example that I have in mind is the following. Look at this guy here. So we would like to find the limit as x approaches 0 of x times ln of x. Well, let's see. So what do we have? It's clear that we're dealing with the indeterminate form infinity times 0, because as x approaches 0, ln of x, x will approach 0, ln of x will approach, depending from the left, from the right, will approach infinity, positive, plus, minus infinity. So we're dealing with the indeterminate form infinity, 0 times infinity. So maybe we can make this limit look like something. So what should we do here? So maybe we can rewrite this in a much more convenient way. And well, instead of a product, maybe we can write it in this way. We can write this as the limit as x approaches 0 of ln of x over 1 over x. And clearly now, as you look, this will have the indeterminate form will be infinity over infinity at this point. So well, now we're in a good position, and we can apply L'Hopital rule. Great. So in our case, we'll have these functions. So f of x is ln of x, and g of x is 1 over x. So f prime of x is 1 over x, and g prime of x is a negative 1 over x squared. Great. So let's do that. So as you can see, we write it in this way. And once we apply L'Hopital rule, so this limit, this will give us the limit as x approaches 0 of 1 over x over negative 1 over x squared. Well, we don't need to apply L'Hopital rule. We can just do the algebra, because this will give us, this will be equal with the limit as x approaches 0 of negative x, and then we can easily plug it in. This will be the limit as x approaches, it will be negative 0, which is 0. And there we go. Right? So this is how we deal with the indeterminate form infinity times 0. We can make it look like infinity over infinity. So instead of writing the as a product, we can write this as a quotient. Great. Let me see another example. And the other example I have in mind is the following. And pay attention here. This is a bit, we need to be careful here a bit. So we would like to find the limit as x approaches pi over 2, but from the left, of x minus pi over 2 times tangent of x. First, let's see, why do we deal with this indeterminate form as 0 times infinity? Well, as x approaches pi over 2, clearly tangent of x will go to infinity, and x minus pi over 2 will go to 0. Great. But can we make it look like maybe, I don't know, maybe infinity over infinity, or maybe why not 0 over 0? Maybe it's much more convenient to make it look like a 0 over 0 type of limit. So what should we do here? Well, maybe we can just rewrite this in the following way. So I can rewrite this as the lim as x approaches pi over 2 from the left of x minus pi over 2 over 1 over tangent of x. But guess what? This 1 over tangent of x is cotangent of x, so this would be the lim as x approaches pi over 2 from the left of x minus pi over 2, everything over cotangent of x. All right, great. So at this point, if we plug it in, this will approach 0 as x approaches pi over 2 from the left, and this guy will approach 0 as x approaches pi over 2. And we deal with the indeterminate form 0 over 0. So we have rewritten infinity, the indeterminate form infinity, 0 times infinity as 0 over 0, right? So that's what we did. All right, great. So we're going to take the derivative of each one of them. So let's rewrite it here. So the two functions are, so f of x is x minus pi over 2, and the derivative clearly is 1, and g of x is cotangent of x, and g prime of x is nothing else than negative cosecant square, right? All right, so we have this. So let's deal with it. So by applying L'Hopital rule, the derivative of this is 1, as you can see it here, right? Then the derivative will be negative cosecant squared, as you can see it here. So we have this here. So by applying L'Hopital rule here once, LH. And now we can plug it in, and we easily see that this is nothing else than just the limit as x approaches pi over 2 from the left of negative sine squared of x. And now if we plug it in, if we plug in x equals pi over 2, then we'll deal, this will give us negative 1. So that's the result of our limit. So that's it, negative 1. Right? So as you can see, this was another example of an indeterminate form, infinity time 0 times infinity, or anyway, infinity times 0. But instead of writing it as an infinity over infinity, we wrote this as a 0 over 0. It was much more convenient for us to do it this way. Because as you can see, we could easily could have taken the derivatives. All right, great. Now let's see some other indeterminate forms, because we said there are 5 extra, or 5 more besides those first 2. So now we have seen only one of them, infinity times 0. Now let's see another one. So we would like to see another indeterminate form, infinity minus infinity. Like I said, this is will not give you 0, so it's an indeterminate form. And the example that I have here is the following. So we need to find the limit as x approaches pi over 2 from the left, again, of secant of x minus tangent of x. All right, great. If we plug in x equals pi over 2, secant of pi over 2 will go to infinity, and the same goes for tangent of pi over 2. So we're dealing with infinity minus infinity, indeterminate form. So we will like to rewrite this, maybe make it look like 0 over 0 or infinity over infinity. So what should we do? First, let's see who secant is. Maybe we can do some algebra here. First of all, this will be the lim as x approaches pi over 2 from the left of secant is what? Is 1 over cosine of x minus tangent of x is sine over cosine. Well, great. And now this will be nothing else than just, this is, let me write it here, the limit as x approaches pi over 2 from the left of 1 minus sine of x over cosine of x. And this is what? Well, as you can see now, we clearly have an indeterminate form, since as x approaches pi over 2, sine of pi over 2 will be 1. So we'll have 0, 1 minus 1, which is 0, and the cosine of pi over 2 is 0. So the indeterminate form that we will get here will be 0 over 0. Great. So at this point, we're in a very good position to apply L'Hopital rule. So let's consider these two functions, 1 minus sine of x. So f is 1 minus sine of x, and g is cosine of x. So f prime of x is negative cosine of x, and g prime of x is negative sine of x. All right, great. So we have the derivative of this. So let's apply the L'Hopital rule. So we have this in this indeterminate form, and by applying L'Hopital rule here, we're going to take the derivative. So this is what we applied here. So on the top, we have negative cosine of x that you guys see it here. And on the bottom, you have negative sine of x that you see here. Well, this is nothing else than just 0 over 1, which is 0. So again, this is another example of an indeterminate form, infinity minus infinity, which will give you 0. All right, beautiful. I hope this makes sense. Let's see another example. Look at this beauty here. So we like to see, I think this is one of your online homework, if I'm not mistaken, but anyway, it doesn't matter. You have plenty of examples of this type involved of this limits in your online homework, so have fun with that. So we need to find the limit as x approaches 0 from the right this time of 1 minus x minus 1 over sine of x. Okay, that's great. So what should we do here? As you can see, if I plug in 1 over x as x approaches 0 from the right, will be positive infinity. And the same goes for 1 over sine of x as x approaches 0 from the right. It will be again positive infinity. So we're dealing with infinity minus infinity at first. But maybe there is something we can do so that we can make this limit look like 0 over 0 or infinity over infinity. So let's do that. Maybe we should do some algebra here. So let's see. So this would be the lim as x approaches 0 from the right of, so what do we have on the top? So it will be sine of x minus x over x times sine of x. All right, great. Maybe we should consider f of x to be sine of x minus x and g of x to be x times sine of x, their product. So the derivative, at this point, if we plug it in, we'll have 0 over 0. So let's look at this. So sine of 0 is 0, minus 0 is 0. So the indeterminate form, this would be 0 over 0. Great. So we're in a good position to apply L'Hopital rule, but first let's compute the derivative. So that will be cosine of x minus 1, and g prime of x will be, oh, we need to apply the product rule here. So let me write it like this. Oh man. Let me write it here. So g prime of x by using the product rule, so it will be sine of x plus x times cosine of x. Great. Great. So let's compute these. So our first application of the L'Hopital rule will give us this, right? So again, we apply here L'Hopital rule. So as you can see on the top, we have the derivative of f. So the derivative of sine of x minus x, which is cosine of x minus 1. And on the bottom, we have the derivative of x times sine of x, the derivative of g, which is by the product rule, you will have it, you see it here. Also, so it's sine of x plus x times cosine of x. Well, let's plug it in again. X equals 0 plus, so 0 from the right. Cosine of 0 is 1, 1 minus 1 is 0, and then on the bottom we have 0. So again, we have indeterminate form 0 over 0, so we can go with another derivative. So let me compute again. So f second prime of x. So we can apply L'Hopital rule one more time. This would be negative sine of x. And here, g second prime of x will be negative cosine of x plus, oh my God, and here we have a product. So it will be, okay, let me write it like this. Plus cosine of x plus plus x plus x times negative sine of x, right? Anyway, and we'll have it here by another application of L'Hopital rule, right? As you can see, the derivative is right here. So this guy here is right, this guy here. And negative sine of x is right here. All right, one more time application of L'Hopital. Right now we can plug it in for 0. Let's see. Sine of 0 is 0. Cosine of 0 is 1. So we have 1 plus 1 plus 0. Great. So it will be 0 over 2, which will give us 0. So the limit of this guy is 0. So we have seen an indeterminate form, which is infinity minus infinity, and by just doing some elementary algebraic manipulations, we made it look like 0 over 0. Let's see another example. Now let's deal with the 1 to the power infinity. So in other words, we need to find the limit as this limit. Let's denote it by L of, and we have said a few things before about this limit, but now we would like to deal with it properly. So we would like to find L, which is given by the limit as x approaches infinity of 1 plus 1 over x, everything to the power x. And we'll see a bunch of examples with this indeterminate form. Okay, let's see. So that's what we need to find. You see here we have a function and power another function. And we have seen when we try to compute the derivative of this, that we take the procedure that we need, the idea that we need to use was just to take the natural log of this expression. Well, also this limit will not make any exception from this idea. But first, before we go into this, into details, let's see why this is 1 to the power infinity indeterminate form. So that's the first thing that we need to see. All right, let's see. So as x approaches infinity, 1 over x approaches 0. So, right, so this guy approaches 0. So we will deal with what 1 to the power infinity. That's obvious. And now guess what? So we'll denote this by L. Like I said, we're going to take the natural log. So take the natural log on both sides. Now, since we know that the function is continuous, so we have no problems using the continuity of the natural log, we can plug in the limit. We can switch the limit with the natural log, so we can plug in the natural log inside the limit, which we did here. So in other words, ln of L will be the limit as x approaches infinity of ln of 1 plus 1 over x, everything to the power x. Great, and now we're going to perform elementary operations on the natural log so that we can make it look nicer. So using the properties of the log, we will end up with finding this limit here. Right, the elementary properties of the log is we're going to take x in front of the natural log. So now what we need to find is this beauty right here. So it's the limit as x approaches infinity of x times ln of 1 plus 1 over x. Great. So that's what we need to do. Well, before we do this, let's see what kind of indeterminate form we have. What kind of indeterminate form we're dealing with. Well, as x approaches infinity, ln of 1 plus 1 over x will approach ln of 1, which is 0. So we're dealing with the indeterminate form is infinity times 0. So we will have to make this one look like something like 0 over 0 or infinity over infinity, and so that we can apply L'Hopital rule. Great. So what we can do, we can write it in this way, as we have seen previously in a previous example with that natural log and the cube root of x. So let's write it in this way. So this product, or also with there was this limit as x approaches 0 of x times ln of x. So we're going to do the same trick. Well, trick, whatever. So we're going to perform the same thing. So we're going to write it as the limit as x approaches infinity of ln of 1 plus 1 over x, everything over 1 over x. Great. And at this point on, if you take x large enough, 1 over x will approach 0. So this on the top you have ln of 1, which is 0, and on the bottom you have 1 over infinity, which is 0. Great. So we can apply, so in this, at this point on, we can consider these two functions. So let me write them here. F of x is ln of 1 plus 1 over x, and g of x is 1 over x. So what we need to do right now is just to take the derivatives of these two functions. So f prime, let me write here, f prime of x is what? 1 over 1 plus 1 over x times 1 plus 1 over x prime, which is negative 1 over x squared, right? I don't think I made any mistake. And g prime of x, let me write it here again. G prime of x is what? Is negative 1 over x squared. Great. So these are the derivatives. So we'll plug these two in. And guess what? Look, by applying L'Hopital rule once, so here we apply L'Hopital rule. So the derivative, the limit as x approaches infinity of f of x over g of x is the limit as x approaches infinity of f prime of x over g prime of x, right? As you can see them right there. And now by just doing some algebra, we will end up with this. The limit as x approaches infinity of 1 over 1 plus 1 over x, which is 1 over 1, which is 1. So now we have that ln of 1, ln of L, because keep in mind that we started from here. We took the natural log. It's not the result of the limit itself. It's the result of the natural log of the limit. So since the result is 1, since ln of L equals 1, then L will be E. So we need to solve this equation. And once we solve it, it will give us that L equals E, the base of the natural log. So in other words, we have this big result, big, beautiful result right here. And in fact, let me write it again. I'm going to write it here. The limit as x approaches infinity, and that's a good thing for you to know, of 1 plus 1 over x, everything to the power x, is E. This mysterious number E. So that's what you need to know. Right? So that's the procedure for finding this limit. Now let's see more examples of indeterminate with indeterminate form 1 to the power infinity. Okay, let's see another one. Look at this beauty here. So we need to find the limit as x approaches 0 plus, right, of 1 plus sine of 4x, everything to the power cotangent of x, right? Again, if we look at this, right, If we plug in x equals 0, you see sine of 4x will approach 0, and cotangent will approach infinity, right? So we're dealing with indeterminate form 1 to the power infinity, and we're going to do the same thing. So we have power to power another function, right? So we're going to take the natural log here, and once we do this, so take the natural log on both sides. And once we do this, and we're going to use the continuity of the ln, we're going to swap the limit with the natural log. And by just doing operations, properties of the log, we're going to end up in the same way with the indeterminate form. And now let's be careful. So as x approaches 0 from the right, cotangent of x will approach infinity. And ln of that will, ln of 1 plus sine of 4x will approach ln of 1, which is 0. Great. So at this point on, we can consider, we have infinity over infinity. So we have to make it look like some kind of a 0 over 0 or infinity over infinity. So we have two options here. So we either go infinity over infinity, or we can go with 0 over 0. But as you can see, I can deal easier with 0 over 0 because I can take the cotangent on the bottom and I can write it 1 over cotangent, which is tangent. So I can write it in this way. And at this point, we have the indeterminate form is 0 over 0. And we are in a good position to apply L'Hopital rule. So therefore, I can take these functions. F of x is ln of 1 plus 10 sine of 4x. And g of x is tangent of x. So what we're going to do is we're going to compute the derivative of these two functions. So let me see if I have enough room here. Let me write it here. So maybe I should put them here. So f prime of x is 1 over 1 plus sine of 4x, right, times 1 plus sine of 4x prime, which is 4 times cosine of 4x. Great. And g prime of x, so the derivative of the tangent will be secant squared. All right, so we have the derivatives of these two here. Great. Great. So now we're in a good position to apply L'Hopital rule. As you can see, we can do it easily. So by applying the L'Hopital rule, this will be the limit as x approaches 0 from the right of 1 over 1 plus sine of 4x times 4 cosine of 4x, everything over secant squared. And now we can we can do some algebra here, right? And by just doing some algebra, we're going to end up with this guy. So it's the limit as x approaches 0 plus, so 0 from the right, of 4 times cosine of 4x, everything over 1 plus sine of 4x times everything times secant squared. Well, clearly the top will give us 4, and the bottom will give us 1, right? So it's 4 times 1 over 1 plus 0 times 1. So the result will be 4. But let's not get ahead of ourselves. This is not the final result. Keep in mind that we started with ln of L, and we ended up with 4. So this means that ln of L is 4, so L will be e to the power 4. In other words, this limit right here is e to the 4th. That's the final result. Right? All right, we're not done yet. I know this is a little bit of a longer lecture, but I want to cover as many applications as possible so that I can get rid of L'Hopital rule. And as you can see, I'm not going fast enough, so because I want you to grasp all the things that we cover in this lecture and all the techniques and everything. so that you wouldn't have any problems with this when at the final exam. All right, now let's see another indeterminate form, 0 to the power 0. And at this point, we would like to find this limit. So find this limit. L is the limit as x approaches 0 from the right of x to the power x. Well, if we plug it in, clearly we get 0 to the power 0, so there is no point of giving more explanations about this. It's pretty clear. And again, we're going to do the same thing. So we're going to take the natural log, so let's do it. Take the natural log on both sides. We'll get that ln of L is ln of the limit as x approaches 0 of x to the power x, so we're going to get like this. Well, since ln is continuous, so we can swap the limit with ln. So we're gonna end up. We're gonna have the limit as x approaches 0 from the right of ln of x to the power x, right? So it's ln of this, and again x will go outside. So we're gonna end up with this. But keep in mind, remember we talked about this function, about this limit previously. This guy here. We actually computed it, and we said that this is actually 0, right? Let me go back. You see? It's right here. It's the limit as x approaches 0 of x times ln of x. Well, in this situation, we will deal with the limit as x approaches 0 from the right of x ln of x. So the same thing goes. So we're going to write this in the form of infinity over infinity, so that we can apply L'Hopital rule. And then again, the same thing goes. We have this function, ln of x, and g of x is 1 over x. And I did this, so let me just write it again. This is 1 over x, and g prime of x is negative 1 over x squared. So this is it. All right, so we apply L'Hopital rule, so we'll get this, and this will be the limit as x approaches in the end, as x approaches 0 from the right of negative x, which will give us ln of L is 0, and thus L will be e to the power 0, which is 1. So this limit here is 1. So this is how we deal with it, right? Again, we started with the indeterminate form 0 to the power 0. We managed to, by taking the natural log and using the properties of the log, we managed to rewrite this as the infinity over infinity indeterminate form, and then we can apply L'Hopital rule. There's another example that I could quickly go over. And again, instead of finding the limit as x approaches 0 from the right of x to the power x, I can modify this by, and in fact, I did this in the midterm exam, but I asked you for a different thing to compute the derivative. We can just modify it a bit. Instead of x, we put sine of x, and we're going to do the same thing. So I'm just going to show it to you directly, and I'm just going to go over quickly. So again, we take the natural log of the limit. You're gonna using continuity of ln and the properties of logs. You're going to end up with this guy here. And again, this will be infinity 0 times negative infinity indeterminate form. So maybe we can write this as infinity over infinity. And then when you consider these functions, f of x is ln of x, and g of x is cosecant of x. So f prime of x is 1 over x, and g prime of x is, well, cosecant of x is a negative cosecant of x, times cotangent of x. So these are the derivatives. We're just going to apply L'Hopital rule here, and then we're gonna obtain this one here, obtain this limit, and now you just do the algebra, and then this will be equal to the limit as x approaches 0 of negative sine squared of x over x cosine of x, and then this will give you 0 anyway. I'll leave this to you as an exercise to figure this one out. So ln of L is 0, and this will imply that L will be e to the power 0, which is 1. So the limit of this guy is 1. All right, great. Let's see another indeterminate form. We're not done. We still have one more to do. So what if I would like to find the limit of this guy here? You see, instead of finding the limit as x approaches 0 of x to the power x, I can modify this and I can say, what is the limit as x approaches infinity of x to the power 1 over x? Well, let's plug it in. Let's plug in infinity first. So we have that this is infinity to the power 1 over infinity, which is 0. So this is the indeterminate form is infinity times to the power 0. All right, great. No problem. We're going to do the same thing as we have done before when we dealt with 1 to the power infinity. We're going to take the log on both sides. So we will get that ln of L is ln of the limit of x to the power 1 over x, right? And now we're going to use the continuity of the natural log. So we're going to swap the limit with the log, and we're going to end up with this. Using the properties of the logs, we're going to end up with this limit. So we would like to find the limit as x approaches infinity of 1 over x times ln of x. But we can easily write this just in this way. And at this point on, we are in a very fortunate situation because we can write this as the limit as x approaches infinity of ln of x over x. And this is a infinity over infinity indeterminate form. So let's just take f of x to be ln of x and g of x to be 1 over x. Oh, sorry, x. I'm sorry for that. Clearly, the derivative f prime of x is 1 over x, and g prime of x is 1. So we're going to apply L'Hopital rule here, and then we can easily see that. So that this will be the limit as x approaches infinity of 1 over x over 1. And this is clearly 0. So ln of L is 0, and therefore L will be e to the power 0, which is 1. So again, this is equal to 1. Great. Now let me tell you something. So we have seen a bunch of examples, but now let me tell you, let me draw your attention with two more things, and then I'll stop. So as you have seen a bunch of examples with limits which involve natural log or the exponential, right? So generally we have this. And now going back to that tower of power of functions, right? And since we said that some of them, all of these functions for x large enough will cross the infinity line, but some of them will cross it faster than others. Well, I would like to address this so that I make myself very clear. And we have seen an example in this lecture when we computed the limit as x approaches infinity of ln of x over cube root of x, and we have seen that that was 0. In fact, we have the following limits. So using L'Hopital rule, one can prove the following. And this is important. I would like you to know this. So for positive integer numbers k and n, we have these four limits, right? So the first one is the limit as x approaches 0 from the right of ln of x over x to the power n. This will give us negative infinity. As you can see, because x approaches 0 from the right, I want you to pay attention. See, there is a difference between the first and the second one. So the second one is the limit as x approaches infinity of ln of x over x to the power n, which will give us 0. So pay attention here. This is the difference here and here. And then we can say the same thing for the third and the fourth one. So the limit as x approaches infinity of e to the kx, right? Everything over x to the power n, that's infinity. And the limit as x approaches infinity of x to the power n, everything over e to the power kx is 0. So these are the two limits that I would like you to have a very good look at, because this will be important. And now, let me just draw your attention with one more example, and I think I will stop. It wasn't in my intention to make the lecture pretty long, but so the last example that I would like to do in this lecture is the following. So I would like to evaluate the limit as x approaches infinity of e to the negative x times square root of x. First, let's see what kind of indeterminate do we have. What kind of indeterminate form? So as x approaches infinity, e to the negative infinity is what? Is 0. So it's 0 times it's 0 times infinity. So that's the indeterminate form. Great. So no problem. Maybe we can rewrite this in a certain way so that we could make it look nicer. And yes, we can do it because e to the power negative x is 1 over e to the x. So we can write this limit in the following way. So we can say that the limit as x approaches infinity of e to the negative x times square root of x is nothing else than the ratio between square root of x and e to the power x. Beautiful. And now as x approaches infinity, clearly on the top we have infinity, on the bottom we have infinity. We're in the best position to apply the L'Hopital rule. So in this case, the functions f of x is square root of x and g of x is e to the x. Quite clear how to compute the derivatives of f prime of x is 1 over 2 root of x, right? And g prime of x is just e to the x, so it will stay the same. So by applying L'Hopital rule, as you can see here, anyway, we can write this as 1/2 times x to the negative 1/2, everything over e to the x. So here I apply L'Hopital rule. And now, guess what? I'm going to take out 1/2, and I'm going to put everything on the bottom. And as x approaches infinity, this guy here, only this guy here, will approach infinity. So the whole limit will be 0. So it will be 1/2 times 0, which will give us 0. So the value of the limit is 0. So this was an easy one. All right, I think I'm going to, this is pretty much what I wanted to cover in today's lecture. Like I said, I apologize for being so long. But anyway, I think it's very important for you to grasp all these techniques and how to use them. Like I said, you'll have problems of this kind at the final exam. And since the final exam is going to be like a multiple choice, I think it's better, it's good for you to have some exercise with these. All right, I guess I'll see you on Wednesday. Happy Easter, everybody. Take care, bye-bye.